Telecom networks are changing again, and this time it's not about faster speeds or better coverage, it's about turning networks into intelligent, software-driven systems.
Somewhere in a laboratory in Nanjing, Chinese engineers pointed a transmitter at a receiver and sent data through the air at 206.25 gigabits per second. No cable, no fiber, just air. At that speed, you could download an enormous amount of high-definition video in seconds. Then another Chinese team went even further. In a trial network north of Beijing, researchers reported a peak downlink of around 1 terabit per second. That's roughly 100 times faster than typical 5G. And here's why that number matters. 1 terabit per second is the performance target set for the next generation of mobile networks. A target that wasn't expected to become practical until around 2030 was already being demonstrated years earlier. Then, in March 2026, China announced that the first phase of its national 6G trial program was complete. 4 years of work, 302 core technologies, terabit per second peak rates, and extremely low latency. But this story isn't really about speed, it's about whether 6G can succeed where 5G failed. The 5G problem. Back in 2018, 5G was sold as much more than faster phones. Governments and telecom companies promised autonomous vehicles, remote surgery, smart factories, and an entirely connected world. The money followed. Between 2018 and 2024, telecom operators worldwide paid governments more than $150 billion for spectrum alone. Then came the cost of actually building the networks. And what did consumers get? Faster phones, better video streaming, and fixed wireless internet that genuinely helped in some places, but the revolutionary applications never arrived at the scale promised. Remote surgery didn't become routine. Autonomous cars didn't suddenly depend on 5G. And there was no killer application that made consumers willing to pay dramatically more. The telecom industry had spent enormous amounts of money upgrading the network, but its revenue barely changed. And that created a problem for 6G. Why spend hundreds of billions again if 5G didn't create the business revolution everyone promised? The physics problem. There's another reason 6G is difficult. Radio frequencies have a trade-off. Lower frequencies travel farther and pass through obstacles more easily. Higher frequencies can carry vastly more data, but they don't travel as far. They can be weakened by rain and humidity. Walls can block them. Even a person standing in the wrong place can interfere with the signal. 5G already discovered this problem with millimeter wave technology. The speeds looked incredible in laboratories, but covering real cities required dense networks of small cells. And that's expensive. 6G wants to go even higher, into the terahertz range. The reward is enormous bandwidth, but the physics becomes brutal. So how do you make it work? The terahertz bet. The answer is beamforming. Instead of broadcasting a signal everywhere, engineers use arrays of tiny antennas to create an extremely narrow beam aimed directly at the receiver. Think of the difference between shouting across a room and pointing a laser. At terahertz frequencies, engineers can pack huge numbers of antenna elements into tiny spaces. But now the network has another problem. That incredibly narrow beam has to follow a moving device while constantly avoiding obstacles. So 6G isn't simply about transmitting faster. It requires the network to understand where devices are, how they're moving, and how the environment is changing. And this is where one Chinese breakthrough may matter more than the speed records. The chip. In 2025, researchers from Peking University, City University of Hong Kong, and collaborators built a tiny chip measuring roughly 11 millimeters by 1.7 millimeters. Its remarkable feature, it could operate across frequencies from 0.5 gigahertz all the way to 115 gigahertz. Traditionally, covering that range would require multiple separate radio systems. This chip uses photonic technology to handle much of the processing with light instead of conventional electronics. It can achieve data rates above 100 gigabits per second and retune frequencies in around 180 microseconds. Why does that matter? because the biggest breakthrough may not be faster wireless, it may be cheaper and simpler wireless hardware. If technology like this can be manufactured at scale, a single component could replace much of the complexity currently spread across multiple radio systems. The speed records grab headlines, the chip could change the economics, and economics determines whether technology actually gets deployed. Why China is ahead? This is where the bigger story begins. China has become the world's largest source of 6G patent applications, accounting for roughly 40% of global applications in the first half of 2025. Huawei alone holds thousands of 6G-related patents. China Mobile holds many more. And unlike a fragmented research effort, China's IMT 2030 program coordinates telecom operators, equipment manufacturers, universities, and government agencies. The physical infrastructure is already enormous. By mid-2025, China had around 4.55 million 5G base stations and more than 1 billion 5G subscribers. That infrastructure becomes the foundation for whatever comes next. China has also moved early on spectrum allocation and is experimenting with satellite-based 6G, integrated sensing and communication, and AI-native networking. And one of those ideas may finally provide the application 5G never found. 6G that can see. Imagine a network where the radio signal isn't only carrying your data, it is also sensing the environment. The same signals used to communicate could bounce off objects and return information about their surroundings. In effect, a base station could start behaving like radar. It could detect movement, track objects, map spaces, potentially even detect whether someone has fallen. And Chinese researchers have demonstrated wireless control systems where extremely low latency is essential. That could matter far more than faster Netflix. Factories currently use physical cables because wireless isn't reliable or responsive enough for critical industrial control. If 6G can deliver extremely low latency and ultra-high reliability, wireless could finally replace some of those cables. That is a real new capability. But 6G is not one yet. China may have impressive laboratories, patents, and infrastructure, but that doesn't mean China has already won 6G. Because 6G isn't just a technology, it's a global agreement. The standards are being developed through international organizations, with major specifications expected around 2029 and commercial deployments targeted around 2030. And the standards matter because whoever's technology becomes part of the global standard can gain enormous influence and potentially billions in licensing revenue. That's why Japan, South Korea, Europe, and the United States are all investing heavily in 6G research. The race is not over, and there are still huge problems. A terahertz demonstration between two fixed points is not the same thing as covering an entire city. Terahertz signals don't travel far. Rain, humidity, and walls can disrupt them. A real 6G network could require extremely dense infrastructure, and that creates the same economic problem that hurt millimeter wave 5G. Then there's the biggest question of all: who pays? Telecom operators are still dealing with the enormous costs of 5G. They have little appetite for another expensive generational upgrade unless customers and businesses actually pay for it. So here's where the story stands. The technical achievements are real. 206 gigabits per second is real. Terabit per second trials are real. China's 6G research program is real. And the new radio chips may be even more important than the speed records. But 6G is not the end of 5G. 5G will remain the foundation of mobile connectivity for years. The two generations will develop together. And the biggest question isn't whether engineers can make wireless communication faster. They clearly can. The real question is, what will we actually use all that speed for? Maybe industrial robots, maybe sensing, maybe autonomous systems, maybe an application nobody has invented yet. Because until that application exists, the world's fastest wireless connection is still a very impressive answer to a question the market hasn't asked.